So we'll start with aldehydes and ketones today. See, in aldehydes and ketones, first part we need to know is about the nomenclature, common names, and IUPAC names. Most of these have various common names, which we use it very regularly in the questions as well. Like HCHO is formaldehyde. This is acetaldehyde. Okay. Then this one is cinnamaldehyde. This one is acetone. This is benzaldehyde. Then this representation is vanillin. This is salicylaldehyde. The last two, these two are important. This is read as acetophenone and benzophenone. Acetophenone and benzophenone. And lastly, this is a furan based aldehyde known as furfural. Alright. A part of it, pivalaldehyde, mesetaldehyde, mesetyl oxide, furone, phthalaldehyde. These are all the terms that will keep on coming across. So please make sure that you have this page ready with you. Okay. uh, I mean, at least while solving, you should, if you have this, you'll be slowly able to learn the terms. Correct. Now let's see how the preparation works. Correct. So preparations of carbonyl compounds from alkenes. Via alkene, you can get aldehydes or ketones using reductive ozonolysis. That is, if you have R, CH, double bond CH, and R dash, so that when you ozonolize in the presence of zinc, so you'll get this as an aldehyde here and an aldehyde here like this. Okay, these are the two aldehyde forms which you can get. One second. We see few examples. Suppose if you have it in a cyclic form like this, and if we perform reductive ozonolysis, on one end we will have an keto group, and on the other end we'll have an aldehyde group this way. Okay. Likewise, in case if you have a double bond like this, performing ozonolysis with zinc, you would get this as ketone, and one CHO bond will be there, and the other one will be HCHO. So three different carbonyl compounds are formed. This is glyoxal, this is acetone, and this is formaldehyde. Clear? Next. The other way of preparing aldehydes and ketones is via Wacker's process. The reagent used is palladium chloride, and we use air and with some moisture, adding with CuCl2. Clear mechanism is never been suggested, but idea is like this. So we have CH2, any alkene. When you treat this with palladium chloride in the presence of O2 and H2O, and promoting that with CuCl2, it will cause an addition type of form and you'll get CH3CHO. So it is like you are adding, okay, OH group to it. So imagine like this, we have CH2 double bond here, and between carbon and hydrogen, oxygen is getting inserted. So if that is the point, how does it appear? It is like CH2 double bond CH and OH. So this is like the enol form which will convert into an aldehyde. So this is a way to remember. Okay. During the reaction, PdCl2 will take up the electrons released and convert that into Pd. Correct? And again, CuCl2, when you treat that with Pd will get oxidized and copper will get reduced. This is what, sorry, copper will get reduced. So this is how the overall reaction will take place. Again, PdCl2 will be reacting back with alkenes. This is Wacker's process. Next one is oxo process, where we have cobalt carbonyl complex. We recently learned how does the cobalt carbonyl process looks like, compound looks like. Got it? So notice that in case if you have any alkene here like this, and we treat this with carbon monoxide and H2 in the presence of cobalt carbonyl compound, that would make it into an aldehyde form like this with H and CHO. Reaction type is like this, where CO and H2 combined together will form H minus and HC double bond O plus. Okay. Now assume as if you are making a Markovnikov addition. That means pi bond will attack here, H minus will attack here. That causes into an aldehyde formation. So this kind of a Markovnikov addition here. So Markov addition will lead to the formation of aldehyde. This is called oxo process. Next is from alkynes. We can use hydration via Kucherow's reagent. We can get aldehydes. Sorry, aldehydes are ketones. Reagent, we know that. So if you have CH triple bond CH and you treat this with HgSO4, we know that it will give you, sorry, CH double bond CH, and it will give you mercuric bridge here, He2 plus. That on hydrolysis, that is with H2O, the attack would happen from here, bond will break from here, we will get CH mercury plus double bond CHOH, and carbon will try to gain back the electrons onto it. So since it is in acidic medium, it will attack on H plus, take away H plus and convert into CH2 double bond CHOH, and Hg2 plus will come out as it is like a catalyst. So you would notice that there is a formation of enol, and the enol will undergo tautomerism to convert into an aldehyde. So that is the final product. In case if you have a substituted group here, and then we are treating that with HgSO4 with dilute H2SO4, in that case ketone will be formed at the center of it like this. This is the keto formation. Got it? It depends upon which is more stable positioning of carbon. So here this is a more stable carb cation position. That is where the water will attack, and eventually you will get this as keto form. Okay. So I hope this part is clear, everybody. Got it? Overall, suppose if at all I have this reaction given, this is a very standard reaction, and I have it like this, and here if you treat this with HgSO4 and dilute H2SO4, what you would notice is that the carbon here adjacent to the phenyl group, correct, so we'll take this H2, and that is what is connected here. So this is major, going on the other side will be minor. But in case if it is only ethyl on one end and methyl on the other end, then you perform Kucherow's reaction. So you have H2SO4 dilute H plus. Then chances of getting ketone this way and chances of getting ketone this way, both of them are observed, and almost both of them are 50-50 percentage. If only ethyl and methyl is present. In case if you have a tert butyl on one end and ethyl on one end here like this, in such case again with HgSO4 and dilute H plus, notice on the tert butyl side you'll have a major product here, and this side it will be minor. So this is major. Got it? So these are the standard questionnaires which are asked from Kuchro's reaction. Please check quickly, everybody. If you have a doubt, you can ask me. The next reaction is hydroboration oxidation, which is of a similar line but more like an anti-Markovnikov addition. So where we have a triple bond CH here, and that I can use B2H6, but B2H6 is replaced by SiA2BH. Okay, and that followed by H2O2 and OH minus. And this would give us RCH double bond CH with boron and SiA here. And furthermore, on hydrolysis, on oxidation with H2O2 and OH minus, you will get this into an enol form the way we got earlier. And this enol will undergo tautomerism to finally convert into an aldehyde, RCH2CHO. Now, what is this SiA2BH? So, 1, 2, 3, 4. This 4 carbon is connected to boron here. So, 1, 2, 3, 4 with methyl here and methyl here and one hydrogen. This is secondary isoamyl boron hydride. Okay, so that's the name, secondary isoamyl boron hydride. So in case if you know, if you see this, the role is very simple. It would go up to enol form, but further reduction of aldehydes is not observed because of the bulkiness here. The boron compounds will not be able to reduce these aldehydes again to alcohol. But in case if I was taking B2H6, like if you take B2H6 in THF, which was the actual oxidation hydroboration reagent, followed by H2O2 and OH minus. In such case, the last product would be alcohol, RCH2, CH2OH. Complete, reaction on that would happen again. Got it? Just a second. Right. Check out. So this is about the alcohol form. And so to avoid this form of reduction here, right? From aldehyde all the way, if you reduce one more time, so that will get into this alcohol form. Okay. So that can be avoided, using SiA2BH. Got it? And next, if you have, in this case, H2O2 is not used. Directly reduction would happen towards alcohol here. Okay. So in this case, suppose if you have pH CH2 C triple bond CH3. In that case, if I use SiA2BH and then H2O2 and OH minus, in that case, we will notice that this would mostly form CH2 C double bond O CH3. So ketone would be formed here, but this side, the other side will be major. Okay, not on more of the phenyl side here. Got it? So where there is less donating side, so that direction you will have more product formation. Next, how do we use cold dilute KMnO4, which is Bayer's reagent, to make aldehydes and ketones? Check. Again, we can do this using alkynes. So R, C, triple bond C, and R here with Bayer's reagent, and that would first give you enol formation. I mean the hydroxylation, which means C double bond C here with R, getting this as OH and OH here. So this is hydroxylation. You know that what does Bayes reagent does? It gives a syn addition. Okay. So after this syn addition here, it will undergo tautomerism to convert into R C double bond O. On one side, you'll have an alcohol form OH and R. Okay. So what we are getting here is alpha hydroxy ketones. Okay. So this is where we'll end it. Okay. But if you want to make this into further oxidation, now you cannot use the cold condition, but we can use same reagent here. So same KMnO4 in OH minus, but not the cold condition. In such case, this will get further oxidized into ketonic form here like this, R. Okay. By chance, if it is at the aldehyde form, like R, C, triple bond C, and H is there here, and then you are treating that with Bayer's reagent. In such case, first you will get an enol like this. I mean, hydroxylation happens here, correct? Then tautomerization would happen on the right hand side here, which makes it aldehyde. And Bayer's reagent, when there is an aldehyde, it can further oxidize the aldehydes into acids. So without using some new KMnO4 form, even the same Bayer's reagent will convert all the way to acids. Got it? This is what you would notice out of Bayer's reagent. Okay. Idea is simple. First, you take triple bond, convert into an hydroxylation, and through that we can make tautomerization and convert that into ketones. Next, aromatic aldehydes, that is from benzene. If you want to convert into benzaldehyde, there are multiple name reactions. We have come across this in benzene form already, in the form of Gattermann's reaction, Gattermann-Koch reaction, and so on. Check out. First, Gattermann's reaction. In this case, the reagent that we use is HCN. Got it? HCN in the presence of HCl, small amount of HCl. And either you can take AlCl3 or you can take ZnCl2. Any one of them will be working. The reaction goes like this, where you have H triple bond Cn here. So this would take from HCl. And to break the HCl, we require anhydrous AlCl3. And that's the way it works. So the lone pair present on chlorine will attack here. Lone pair present on nitrogen will attack here. Bond will break here. That would give us, okay. So CH double bond NH here, right, with a plus charge here, because this pi bond will also move on to nitrogen here. So that plus AlCl4 minus. And now comes benzene. Benzene notices that we have an electrophile in the form of CH double bond NH with a plus charge, and pi bond will go attack here, and that will cause benzene to form CH double bond NH, an imine form, right? And this is EAS reaction, electrophilic aromatic substitution. Imines are highly unstable in acidic medium. So that's when, after the imine formation, we add the water or in aqueous solution, it will immediately turn back into aldehyde and ammonia. So that's how you can prepare the aldehyde forms, benzaldehyde. This is Gattermann reaction. Okay. So please recall the same thing we have learned this in benzene before. Okay, this is imine family, imine form. Now, what is Gatterman-Koch? Gatterman-Koch, the reagent that we use here is carbon monoxide with HCl, again with dry or anhydrous AlCl3. The logic is very similar to how we have done it earlier. So C minus O plus, and this can be written in a canonical form as C double bond O lone pair here. Sorry, O plus here. And then in case if you write HCl here and AlCl3, the same thing works here. The lone pair present on chlorine will try to attack as a Lewis acid towards the Lewis acid. C minus will attack on H plus. Here the bond will break. And as it happens, you will get H C triple bond O plus Al Cl4 minus. And benzene notices that there is an electrophile generated in the form of CH double bond O with plus charge. Because if you write the resonating form of this is what we will get. And the pi bond would attack on the carbon, converting that into an aldehyde form. So that's how we will get benzaldehyde. Okay, through ES reaction. Okay, so Gatterman-Koch, this is the product formation. Same aldehyde would be formed in this case. Okay. Next, the third reaction here is called as Etard reaction. Is called as Etard reaction. Etard reaction, the reagent that we use here are chromyl chloride in CS2 followed by hydrolysis. This is followed by hydrolysis. So the reaction here works when we have a toluene here. So CH2H. So this is a toluene. So when you have this toluene, right? And toluene, as you react with chromyl chloride, CrO2Cl2, it will start forming an intermediate here. Okay, so first intermediate will be like this. We'll have benzene with CH, correct? CH2 here. And you can notice that this H is very easily replaceable, and that will start moving towards this oxygen attached to chromium, which is double bond O, correct? Sorry, which is OH. No, double bond O here, and now that is OH has become, sorry, OH. Then we have two chlorines here this way. This is the bond formation which is observed. So basically, it's like this: chromium has Cr, double bond O, double bond O, chlorine, and chlorine. So imagine as if the protonation, the lone pair has taken this H plus, and the carb anion is attacking on the other part of the oxygen like this. This carb anion is attacking here so that the chromium can take the electrons away and oxygen can take electrons away this way. So this is the way it gets connected. Got it? And imagine doing this two times because you have two more hydrogens here. So second mole also, if you react, you will get this as the intermediate. So that is RCH. We will have O connection with Cr, Cl2 and OH. Same O, Cr, OH, Cl2. This way. And now when you perform hydrolysis here, correct? So if you perform hydrolysis, H3O plus, and that would make this CH into CH, OH and OH, which will eventually convert into an aldehyde form. Okay, because as if this plus will come here, I mean H plus will come here, and OH will attack on this carbon. So what you will get here is H2OH and OH here, OH twice, and CrCl2. Like this, we'll get 2 moles. This will convert back into aldehyde by removing water. Okay. Now, problem what happens is whatever the chromium that is forming, right? So that has a chance to again get oxidized further. Okay. So which means whatever the chromium that is forming here, once again, yeah. What are the chromium that is forming here? So you see, we have Cr with two OH groups here, right? And two Cl here, correct? So you can notice that this double bond O will push, remove one chlorine out. So that's how you'll get this as Cr double bond O, OH and Cl. And imagine with water, because it is in water, so that chromium will also go out and you'll get this as OH and OH plus HCl. That chlorine will also go. So what is this becoming? This is becoming chromous acid. Chromic acid has converted into chromous acid now. So chromous acid oxidation state is +4. Okay. So what happens here is H2CrO4, or in this case, what do we have? We have CrO2Cl2. We have CrO2Cl2 plus H2CrO3. H2CrO3 will convert into H2 or HCrO3 this way, where the oxidation state is now +5. It get disproportionated. Okay. And another one will become Cr+3 and 2Cl minus, like this. So a disproportionation is observed where the oxidation state is +5. So this +5 oxidation state group will again attack on the similar way here. So we will get benzene with toluene plus HCrO3 also. That would also on hydrolysis eventually will give us aldehyde, and that chromium will convert into Cr+3. So what is to be noted here, students, is that oxidation initially is +6. Oxidation initially is +6. It will convert into +4. That +4 disproportionate converts into +5 and +3. The +5 eventually also become +3. So overall reaction, if you notice, chromium was +6. Now it has become +3. So till it becomes +3, it will keep on reacting with the toluene part and try to convert into aldehyde. Okay. So this is what happens in ETARD reaction, everybody. Overall mechanism is, overall reaction, what is happening is asked, but not the mechanism. So you don't have to worry about what is the mechanism. Okay. Next. Next is about alternative ETARD reaction. Another alternative ETARD reaction is that in case if we react toluene CH3 with CrO3 directly in the presence of acetate, that is CH3CO twice O, correct? And that followed by hydrolysis. That followed by hydrolysis. And this will give us aldehyde CHO. Okay. Here I will just like to show the intermediate because that is given in NCERT directly. The intermediate which is formed is not with respect to chromium but is with respect to the acetate group. That is CH. We have O, C double bond O CH3 and O, C double bond O CH3. And this is the intermediate which on hydrolysis will eventually give us aldehydes. Benzaldehyde. Okay. So please check out the ETARD reactions carefully. This is given in NCERT and it's very common question how the reaction works in ETARD. Done. Done, guys. Right. And we go to the next part. How do we get aldehydes or ketones using alkyl halides? See, if you have R CH2Cl, that when you react with DMSO, DMSO, that will give you R CH double bond O. Okay. What is DMSO? This is DMSO, dimethyl sulfonate oxide, sulfoxide. And in the case of alkyl halides here, if this is an alkyl halide, then the lone pair on oxygen will attack here and chlorine would attack here. So this creates situation like this where chlorine is here and oxygen gets connected with CH2 and R. Okay, got it. And then uh, let me put it this way. So rather, I'll put it this way: plus charge here, this way. Okay, and Cl minus has lost out. Okay, so now if you want to get this into an aldehyde form here, so first this H plus has to leave. Correct. So which means it will get a negative charge on this part. So Cl minus will take H plus from here, and that will give you sulfur with double bond O plus and CH2, sorry, CH minus and R. And this bond will push here, this bond will go here. Got it? And sulfur will take away electrons on it. Got it? And then oxygen will have a double bond with CH and R with a plus charge. Got it? So now when oxygen takes away electrons, it would simply become a dimethyl sulfur and RCHO and HCl. Okay. So typically this is how the mechanism works. Again, mechanism is just for the reference. Nobody's going to ask you what is going through it. Just you need to remember the fact that DMSO will create aldehydes and HCl will come out of it. Okay. Next. In case if you have two halogens, that is geminal dihalides, that will be even better to make aldehyde. So with DMSO, again it will become RCHO and HCl will be formed plus Cl minus. If you have it on the secondary positions like this, with DMSO, it will turn into ketone form R dash plus HCl. Okay, this is a product formation. Next, from alcohols, how do we get aldehydes from alcohols? This we have learned it from alcohols itself. That is all oxidation reactions where these alcohols will get oxidized to convert into aldehyde, right? So the oxidizing agents which we have learned earlier, that includes CrO3 in acetone, CrO3 in acetone, PCC, PDC, copper and heat, we have learned CAN reaction, Swan's oxidation, Swan's oxidation, bromine water, right? Right? So bromine water and so on. All of these are used as oxidizing agents to convert alcohols to aldehydes. Okay. In case if you have alcohols and if we are converting directly to acids, then the oxidizing agents which we will use here, that implies alkaline KMnO4 or acidic KMnO4. We write that as KMnO4 with H plus, or CrO3 with acetone and dilute H plus, which we call it as Jones reagent. That will help it convert into an acid. If objective was to convert into an acid here. So 1 degree alcohol to aldehyde, these are the reagents, and 2 degree to ketones. So if you have R, CH, OH, and R dash, and then we need to oxidize this to convert into a keto form, RC double bond O R dash. In that case, all of these oxidizing agents will help. All of these oxidizing agents will help. Along with that, the Jones reagent will also help, and KMnO4 H plus will also help. All of this will convert alcohols into ketones, secondary alcohols into ketones. Correct. Notice what are typical JE reactions, which was previously asked, starting with simple one. If you have secondary alcohol and the question is about CrO3 in H2SO4 dilute, this is how it is being given. You would simply oxidize this to ketone and stop. Second, if you have primary alcohol like this, and then Jones reagent is being used, you will convert that into carboxylic acid. If PHCH2OH is given, that is benzyl alcohol is given, then you are reacting with Jones reagent. This is an exception. The Jones reagent does not oxidize that easily when there is an aromatic aldehyde forms. Okay, yeah. And if you have a simple alcohol here, and then we are treating that with Jones reagent, it will definitely convert into an carboxylic acid. Another important part of Jones reagent is that it does not alter or disturb any double bond forms present. So the double bond will remain, and here this will become COOH. This is what would happen. Okay. So these are all the repeat reactions, everybody. Everything we have learned it in alcohols. These are all oxidation reactions from there. Next is CAN, cerric ammonium nitrate test. Basically here 1 degree alcohols will be converting into an aldehyde. 2 degree alcohols will convert into ketones. Okay. Suppose I have RCH2OH, treating that with complex cerium ammonium complex, cerium nitrate ammonium complex. So this is a yellow color solution which after treatment will convert into R, CH2O, CE, NO3 5 times, and that with 2 minus plus H plus plus NO3 minus. Okay. Now this would be red in color. So the red color change itself suggests that there is an aldehyde form. And from here, eventually it will get oxidized into aldehyde. Okay. And cerium plus 3 complex will be formed, which will become colorless. One important part about this reaction is 1 degree, 2 degree will give color. First, it will become red color and eventually it will become colorless. While 3 degree alcohols like R, C, R, and R and OH. This 3 degree alcohol, when you react with this CN test here, so CO3, 6, 2 minus. In that case, it will form a complex and after that, nothing will change. So it will remain at the complex form. So red color. So further decolorization is not observed. So if the red color remains, that means it is of 3 degree alcohols. If the red color decolorizes over time, it must be 1 degree or 2 degree alcohols. Okay. X2 in the presence of KOH, Cl2 in the presence of KOH, any of this, okay, in basic medium. In basic medium, you would notice first, in case if you have something like an alcohol like this, which has no methyl, directly open methyl, in that case, bromine in the presence of NaOH will only convert up to aldehydes. But same thing if you have an alcohol with a methyl group present on it like this, then the same bromine in NaOH will give haloform reaction. Haloform reaction is when this will become acid and that methyl carbon will convert into this methyl carbon will convert into haloform. Okay. So this happens even when you have this happens even when you have uh, tertiary on one side and methyl on the other side like this. So here this, if you treat with X2 and NaOH, you will get this as COO minus and CHX3. But if it is tertiary alcohol itself, then there is no reaction. X2 and NaOH, in that case, we will not see any reaction happening. Done. This is a reaction with halogen, halogen in basic medium. Swan's oxidation. I gave you an idea about what is Swan's oxidation already. I mean, we just need to know what exactly it does. That is 1 degree alcohol. It will convert into an aldehyde form. 2 degree alcohol will convert this into a keto form. Got it? The reagent that we use to make it is first DMSO with this is an important compound Cl C double bond O Cl like this in tertiary amine. This compound which I have written, this is called oxalyl fluoride. Oxalyl fluoride. So if you use this oxalyl fluoride, then 1 degree converts to 1 degree converts to aldehydes, 2 degree converts to ketone. Got it? Next is Oppenheimer's oxidation. Oppenheimer's oxidation is simply a reverse of MPV reduction. We have seen this in MPV reduction form. Suppose if you have RCHOH and R dash, a 2 degree alcohol, and that has been added with some ketone, especially acetone, and then we have aluminium isopropoxy group added and heat. This will convert into R C double bond O R dash plus this ketone will convert into an alcohol, right? So this is the way the reaction works. This get oxidized to form the keto part and the other reagent, which is ketone, will convert into alcohol. So it's like an exchange reaction. If you do the reverse one, that is, if you take a ketone and convert that into an alcohol, we read this as MPV reduction. Okay. While when you show it as an oxidation reaction, it is Oppenhier's oxidation. Right. The next reaction is with MnO2 and heat, which is causing an allylic oxidation. That is, if you have an allyl alcohol and we treat this with MnO2 and heat, any allyl alcohol will convert into an aldehyde, or any benzyl alcohol will also convert into an aldehyde. So imagine we have like this and we have OH like this. And then if at all I treat this with MnO2 and heat, only the alcohol part will convert into benzyl part will convert into an aldehyde, but the other alcohol will not get impacted. So MnO2 only oxidizes the allylic part. Okay. So which means if you have a ketone like this, alcohol this way, and another alcohol like this, and then I'm treating this with MnO2 and heat. So only the part where it is at a benzylic form that will convert into ketone. This is the product formation. Please notice everybody. Please check. All of these are repeated ones. I hope you're able to recall. If not, at least check this time. What are all the reactions that are common in both aldehydes and ketones? Done? Next. From cyanides, how do we get aldehydes? Right? There are multiple reactions. The first of a kind is Stephen's reduction. Stephen's reduction is when we take cyanides or nitriles, convert that into aldehydes. Well, how are we doing that? Check. We have SnCl2 plus 2 moles of HCl. Tin will undergo oxidation. So it will convert to SnCl4 and 2 moles of nascent hydrogens. Nascent hydrogens would make nascent hydrogen would make an addition here, convert that to RCH double bond NH. Okay, so this is an imine form. So imine is formed. And once you get an imine, double bond NH, the lone pair on it, with SnCl4 plus 2 moles of HCl. So that will convert into RCH double bond NH2 here with a plus charge, and that twice it will add 2 times to convert into SnCl6 overall 2 minus. So it will form a tin complex with a hexadentate. And this on hydrolysis, now it will convert into an aldehyde form. Ammonium will be separated out and tin hexachloride will be separated out as complex. So that's how we will get an aldehyde form in this case. So this is Stephen's reduction. Okay. So guys, any cyanide form, you will get this product. So in case if you have anything, so we have CN here, cyanides. If you react with SnCl2 and HCl here, followed by hydrolysis. So then we'll get aldehyde plus ammonium form. Okay. This, sorry, this is about Stephen's reduction, everybody. Next is dival H. So check out dival H. See, by default, first you need to understand one thing. Dival H is specifically used to convert cyanides, esters, acid chlorides, all of them, right? If we use it with dival H at minus 78 degrees Celsius, it will convert into an aldehyde. Okay, this is the whole idea about dival H. Okay, so typically, if you take cyanides also, for example, C triple bond N, and dival H, right, is H minus provider. So this H minus will go attack here. This bond will move, and you will get this as R CH double bond N minus. And of course, this minus will be connected with that aluminium R2 plus. Okay, so this is how it will get connected. And once you get that here on hydrolysis, we will be able to convert into this into an aldehyde form. This is what has been happening. Of course, if you go beyond minus 78 degrees, that means if you go at 0 degrees or 10 degrees or 25 degrees or slightly heated, then aldehydes will also convert into alcohols. But usually, if temperature is not mentioned, by default, it meant that we are talking about aldehyde formation only. Okay, once again. Just as you can. Let's talk about Grignard's reagent. How does that work? If you take cyanides, Rc triple bond N, and then you treat with something like R dash Mgx. So first R minus will attack here, it get into an addition reaction, double bond N minus Mgx plus, and then we have R dash. Further addition on this is not possible. So if you react with again R dash Mgx, nothing would happen. So therefore, it will simply undergo hydrolysis from here and convert into keto form. So that means if you want to convert a cyanide into ketone, then RMJX is the best bet. Okay, so that will help you convert into keto form. Okay, right. See, halogens, we have learned it already. Haloform reaction, we have learned it already. This I gave you just for extra case if you want to go through the reaction once again. Okay, so I'm not going to teach you again. So please go through it. Keep this here only so that you can revise it and see what are the cases where the haloform reaction is observed. Next, check out how do we get the aldehydes from carboxylic acid or its derivatives. So if it is carboxylic acid, first method by which we can get aldehydes or ketones is by dry distillation. Dry distillation of calcium salts. Dry distillation of calcium salts. That is, if you have R CH2COO twice calcium, that on heating, correct, without water, just heating, in that case we will have this as RCH2 C double bond O, CH2 and R, and calcium oxide and carbon dioxide. This is what will happen as a dry distillation. Well, how does the mechanism work here? Notice we have R, CH2, then C double bond O, O minus. The second mole here is R, CH2, C double bond O, O minus, and calcium 2 plus. As you start heating, first this oxygen will show affinity towards calcium and bond breaking will start here. So bond breaking will start here. As soon as that is done, on the other hand, you will see this carbon dioxide will also start getting out by pushing this negative charge here. As soon as that happens, this carbon will start gaining negative charge, and that negative charge will connect onto this carbon as a positive charge. So step by step, if at all I say, what are steps that are taking place? It is like step 1, step 2, step 3, and step 4. And putting all of them together, so what do I get here? I'll get this as R CH2 connected to C double bond O CH2 and R plus CaO plus CO2. Okay, so this is what you would get on dry distillation, everybody. Okay, next. If you notice the examples, other examples in this case, right, starting from CH3, CH2, COO twice, calcium on heating, you would get CH3, CH2, C double bond O, and CH2, CH3 plus calcium carbonate. You can write it as calcium carbonate or you can simply write it as calcium oxide plus CO2. What if you have mix of two different calcium salt, that is CH3, CH2, COO twice calcium plus CH3, COO twice calcium. So one is calcium salt of propanoic acid, the other one is calcium salt of acetic acid. In that case, first we will see the self coupling here. The self coupling will give us the first compound here like this ketone. Another self coupling CH3, C double bond O, CH3. And then we can also get a cross one, that is CH3, CH2, C double bond O, and then CH3. So you can see this is pentanone, this is propanone, and this is butanone. So all three products will be observed. Got it? Likewise, if I take another example here, if you have CH3 COO twice calcium plus H COO twice calcium. Okay, here we'll get CH3 C double bond O CH3, which is acetone, and the self of aldehyde, formaldehyde, I mean formic acid will be formaldehyde, and the cross is right, because this H minus will connect here and the cross is CH3 C double bond O and H. So this is that aldehyde form which you will get. But what you would notice is this will be a poor yield. This is a poor yield. Reason being, in the mechanism, if this has to be only hydrogen, it has to form H minus. Forming an H minus is a very, very difficult task. In fact, that H minus can actually take this H plus and convert into carbon monoxide. So the yield will be weaker. So that is HC double bond O minus and HC double bond O minus and calcium 2 plus. So as I told you earlier, first this would go away. This carbon dioxide will go away. And then this carb anion is supposed to attack here. So it can attack there also and it can take this H plus also. So both are feasible. So which means you can get H2 gas plus carbon monoxide, or you can get H C double bond O H. So these three can be formed. That's why the yield is not good when it comes to formaldehyde. Okay. I hope this is clear, everybody. Right. So see, some cases how we can make the reaction here, that suppose in case if you have an alkene here like this and you are performing oxidative ozonolysis. Oxidative ozonolysis means you are reacting that with H2O in the presence of H2O. So in that case, you will have COOH. Here also we'll get this as COOH. One second. So then you react this with calcium hydroxide. So it will become a calcium salt. So we'll get this as COO minus, COO minus, and calcium 2 plus salt. And now if you make a dry distillation, everybody, so if you make dry distill, you will get this part into ketone here like this. So this is a keto part which you will get carbon dioxide and CaO. This is a product formation. So this kind of questions are usually framed where you will actually get a calcium salt and then the reaction is happening. One more such example which is very familiar, right, is this kind where we have pH and I have OH here like this. Okay. And this has been treated with, Br2 in the presence of NaOH. Sorry, Br2, CaOCl2, CaOCl2. So CaOCl2, when you notice that this is bleaching powder. So when you make a bleaching powder here, the first thing what it does is it will oxidize the alcohol into ketone, and this ketone will undergo haloform reaction because there is a methyl group present here. So that makes it pH convert into double bond OO minus, and this is with a calcium form, so calcium salt will be present. Okay. So once you get a calcium salt here, this plus CHCl3, this is the product formation. That when you make a dry distillation here, so we will get this as PHC double bond O like this with another pH with CaO and CO2. Okay. So remember the standard questions here, how they are being asked. So first you could either use the ozonolysis reaction and then extend this to dry distillation, or you can use alcohol reaction, convert into aldehydes or ketones and then convert into acids, make it into calcium salt form and then get the dry distillation done. Okay. Please notice this once, everybody. If there is a doubt, you can ask me now. Please check properly. The next reaction to get ketones uh, is from decarboxylation. The decarboxylation that can be done very easily just by heating at a slightly higher temperature, I mean more than room temperature. So if you take beta keto acids on heating, you can get this into ketone plus carbon dioxide. Sorry, how does the mechanism work? See, all you need to do, write this structure. You have O and H, correct? And then double bond O here. And now you can notice that this pi bond would make a bond with O and H because of the strong hydrogen bonding that exists between them. And as soon as the hydrogen bonding happens, this bond will break, converting into carbon dioxide. This bond will break, convert into a double bond form. So as that happens, we will see, we will get a double bond and OH, which is an enol form, and carbon dioxide. And this enol form will convert into ketone. The enol form will convert into keto form. That's how you will get the uh, ketones from beta keto acids. Which means wherever there is a beta positioned keto, right, you can always remove out that carbon dioxide. So this is a standard JE question here. Please check. So if you have, okay, sorry, let me do the same thing with beta acids also first, and then I can show you. Okay. So the same thing happens with diacids, beta diacids on heating. So beta diacids on heating, what will happen? See, if you have an acid here, C double bond O OH, and then here we have double bond O OH. In fact, this is called malonic acid. So in case of malonic acid on heating, one side of the acid will convert into carbon dioxide, the other side will become this CH3 part, so CO2. Mechanism is very similar to what we have written it here. So that is C double bond O, O and H here. This side we have OH and O or double bond O here. So you can see the same thing here. This pi bond will make a sigma bond here, push here. This bond will push here. So it will get into an enol form here like this. Double bond and enol and one more OH here, right? This way. And that plus CO2. And this eventually will convert into double bond O CH3 plus CO2. So what are we getting? Carboxylic acids. So this is heating beta keto acids. Okay. So now as an example, if at all I write this, check. What if I have something like, a ketonic group here and I have lots of COOH group. In fact, let me show you how the JE question was asked. JE question was they give all the cyanide groups here, CN, 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 and CN. And then they perform hydrolysis. Okay. Now, when you perform hydrolysis on this case, all the cyanides will convert into acids. So here you will get this as acids, COOH. In all the cases, we will get COOH, COH, COOH, 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 and COOH. This way. And that on heating, you will see this will go away CO2, 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 CO2. All of them are at beta positions. So these four will go, and these two are beta diacids here. So one CO2 will go out from that. So the product what you will get is ketone here and COOH here and 5 moles of CO2. This is a final product. So keep that in mind. So in all these kind of cases, wherever you have keto to be formed, right? So check out for a beta position. So if beta acid is present, at beta position ketone is present, that acid will be easily removed out. Got it? Lastly, even if you have uh, something like CH2N times, and this CH2 is connected with COOH and COOH, and N is 4, 5, 6, sorry, 4 and 5. If N is 4 and 5, in that case, if you heat it, right? If you heat it, here also decarboxylation take place. You'll get ketone when N is equal to 4, and you'll get this cycloketone when N is equal to 5 plus CO2. So this is a product formation, everybody. Done? Check. So this is about beta keto acids. Decarboxylation is very frequent asked question in JEE. Okay. So you must know how it has to be worked out from keto point of view, from acids. If there are two acid groups or beta keto acids we have, how does it work? Okay. Next. See, acid anhydride on heating. If you have acid anhydride on heating, what will happen? That is R C double bond O O C double bond O CH2R here. And this on heating, same thing here. Imagine as if this CO2 is lost. So these two will get joined. RC double bond O CH2R plus CO2. Correct? So on heating, depending upon I mean this side also it can happen. If you have two different chains, you can get two different types of ketones as well. Okay, right. Next, from esters. Esters, you know that R C double bond O O R dash. If you treat with dival H, that we have learned it already, dival H, fall at minus 78 degrees, followed by hydrolysis, that will convert into an aldehyde plus alcohol. And lastly, from acid chlorides, if you take RCOCl, the same dival H, I have written it before, so I'm writing it again. So when you treat that with dival H with minus 78 degrees Celsius, followed by H2O, it will convert into RCHO. Second reaction is called as Rosenmund reduction. Rosenmund reduction. Rosenmund reduction is when you have R C double bond O Cl and you treat this with H2 in the presence of palladium barium sulfate. That means it is a poisoned palladium surface, which we call it as Lindlar's catalyst. So using Lindlar's catalyst, we'll convert that into an aldehyde form. Further reduction of aldehyde is not observed. Okay. Third reaction set is using lithium aluminum hydride with tert butoxy, group. Okay. So this is like LBAH. Okay. Lithium tert butoxy aluminum hydride. So even if you take RCOCl with LBAH, this is an alternative lithium aluminum dival H. It is an alternative to dival H. The product is the same. Okay. Next, using RMGX, Grignard's reagent, but only one equivalent. So RCOCl, if you make a controlled reaction with RMGX, if you make a controlled reaction, you will get this as R C double bond O R. Okay. Ketone would be formed in this case. Everyone clear on that? Few extra reactions. See, notice extra reactions, how the preparation is working. So first, see, if you have CH3 and you treat this with Cl2 in the presence of H nu, but two equivalents are given. So in such case, we will convert this into CHCl2 and that on hydrolysis. Treat with H2O, it will now convert into CHO. So this is one way of getting an aldehyde form. Clear? Or we can have benzene plus RCOCl in the presence of AlCl3. This is Friedel-Crafts acylation. This way we'll get R. So this is Friedel-Crafts acylation. That way you can get ketones. Or we can get RCOCl plus R2-CD. R2- also has a very special nature that it will only convert up to ketones, right? If I take 2 moles will be converted into this and CdCl2 will be formed this way. Okay. These are few extra reactions that we need to know where the preparation of aldehydes has been done. Clear, everybody? So whatever I have discussed, these are all the preparation reactions of aldehydes and ketones. Okay. Now notice chemical reactions. For chemical reactions to understand, what we need to know is that when it comes to a carbonyl group, a C double bond O group is called as carbonyl group. Across carbonyl groups, you'll have two bond angles. This is alpha, this is beta. Because of the double bond form here, that will have more repulsion. So alpha angle is greater than beta. But if you notice the angle here, as these CH3 groups are increasing, the angle across this beta angle will start increasing. As the alkyl groups increase, the beta angle will start increasing. Okay, that is first feature we should know. Second thing is, this is the first thing we should know. The second thing we must know is that when it comes to structure of carbonyl group, see, there is a pi bond existing between carbon and oxygen. But this pi bond cloud, electron cloud, would be much more closer towards oxygen. That's the reason why the cloud would look something like this. So because of the electron cloud more, observed around oxygen's surface, so carbon would get sufficient positive charge, oxygen will get sufficient negative charge. So due to these electronegative differences, you will have high polarity between carbon and oxygen. Correct? So much so we use the word amphiphile for carbonyl groups. Reason being, this carbon can have partial positive charge, oxygen can have partial negative charge. Which means if an electrophile approaches, oxygen can attack. If a nucleophile approaches, nucleophile attacks on carbon. So both nucleophilic addition and electrophilic addition are observed. Hence, it is called as amphiphile. Okay. Next. Third point is about dipole moment. If you notice dipole moment, in case of aldehyde, the dipole moment formaldehyde is found to be 2.3 dB units. But the same if you notice for acetone, this vector between this carbon and carbon also holds a dipole moment. So here and here there is a dipole moment, and result of those two dipole moments will go towards C double bond O. Okay, goes towards C double bond O here. Yeah, and generally what has been observed is that the ketones would have higher dipole moment than aldehydes, and that shows in their boiling point also. So if you compare a similar molar mass of aldehydes and ketones, ketones would always have a dominant boiling point. So you can see this one, acetone has more boiling point than acetaldehyde or than formaldehyde. In fact, if you have acetone compare with acetone compared with propanaldehyde also, acetone will have more boiling point, okay, of comparable mass. Generally, next. See, generally, if you compare the similar molar masses, right, similar molar mass here, then carboxylic acid definitely has the highest boiling point because of strong hydrogen bonding. Okay, because of strong hydrogen bonding, and then Sorry. And then we have alcohols, again due to hydrogen bonding. Then we have amines due to hydrogen bonding. Then comes ketones, aldehydes, ethers, and then alkyl halides also here. Okay, here also I'll put that. We'll get this as alkyl halides, and then comes hydrocarbons in some water. This is not my bottle. Then, so if you compare the boiling point here, check this ketone is more than this aldehyde, and aldehyde and alcohol. Although molar mass is not exactly same here, these two are very much comparable. And then comes this ketone, and this ketone and ethanol are pretty much comparable, and ethers are least when it comes to boiling point. Next, these are some important physical features. Now let's talk about the chemical properties. The main chemical reactions that aldehydes and ketones will offer is nucleophilic addition reactions. So a lot of books use the terminology NAR, nucleophilic addition reactions. Okay, or simply AR, addition reactions. Okay. Sorry. Check. So if you check the case one here, that means if I take a ketone and expect that there is an available electrophile, something like an H plus ions, then first thing you will observe is that the lone pair of oxygen will take H plus or electron plus here. And this happens very fast because of an acid base reaction. And then the nucleophile, if it is approaching, it will come and attack on carbon position, open up the bond here, and make a complete addition. So when is this observed? Whenever you are adding some nucleophile in the presence of acidic medium like this, alcohol or water or acids or cyanides, when we add these components in acidic medium, in such case, you will see when the nucleophile is weaker, this is a type of mechanism that is observed, where first an electrophile will add, and in the second step, nucleophile will get added. Okay. And in any case, the nucleophilic attack is the rate determining step. Second, what if you have a strong nucleophile directly, like Cn minus, R minus, H minus, Cl minus, ammonia, NH2 minus, any of these? Okay, N3 minus, you can take any number of reagents, strong nucleophiles. In that case, the nucleophilic attack is always the first step. Pi bond will get placed here. We'll get this as O minus. Clear? And that O minus will attack on electrophile and finally converts into an addition product. Okay. So this kind of mechanism is often observed in a strong nucleophilic nature. Here, everybody. Now, whether it is a first case where acidic medium is used or second case where directly nucleophile is used, right? Rate of nucleophilic addition always depends upon two important factors. That is, how much is the polarity developed on C double bond O? Okay. Second, is there enough crowding or bulkiness around C double bond O? Okay. So check. If you have C double bond O here, and if there is a Z group here, for example, and that Z group is any of these four, So obviously NO2 is more withdrawing here. Because of its withdrawing nature, the delta positive charge on the carbon increases, and that allows the nucleophile to attack even faster, and definitely rate of the reaction will increase. So in case if there are any withdrawing groups, rate of the reaction will always increase. So let me write down that here. So in this first case, I can say rate of nucleophilic addition reaction in this case would be greater in the case of A, then C, then B, then D. Okay, because methyl and OCH3s are further. Correct. Therefore, more electron withdrawing group present here, more is the polarity. More is the polarity C delta plus. See this case now. Suppose if you have double bond CH, CH double bond O, and that if I compare that with benzene, this way C double bond OH, and then I compare that with CH3, C double bond OH. If this is A, B, and C, you notice this one, due to the strong resonance here, the delta positive charge on the carbon drastically decreases. Here also sufficiently, strong resonance happening, that will also decrease the delta positive charge. So in case if I compare the rate of nucleophilic addition reaction for this particular example, you would notice that C will be greater than B than A. See, benzene does not offer very strong resonance as much as a simple pi bond will offer, because this pi bond giving gets a positive charge which is stable carbocation. But getting a positive charge on benzene ring becomes it turns into more anti-aromatic form. Okay, so that's why you would notice the reactivity is more in the case of C, then B, then A. So these two cases particularly I have given you to understand the polarities impact. So more the polarity, more is the reactivity, or more is the nucleophilic addition reaction. Now let's compare this idea with more examples here. Suppose in case if you have no crowding here, slightly more crowding here, and more crowding with resonance also, because phenyl offers resonance. In that case, rate of nucleophilic addition reaction convert into, okay, if you have A, B, C here, A greater than B greater than C. So that will be ABC. Next, again, this is ABC. If you compare, here this is ketone, here this is phenyl ketone, here this is diphenyl ketone. Okay, so here this is some resonance offered, along with that sufficient crowding is present. Here the resonance is offered from both the ends. Literally, this is hardly going to make any reactions. It's extremely less reactive ketones. So therefore, A greater than B greater than C. This is what you will notice. Similarly, check out this third case where steric factor also impact the nucleophilic addition reactions. So if you have two ketones versus one ketone, sorry, if you have two methyl groups versus one methyl and one ethyl group and two ethyl groups, if you compare, then this would have more amount of uh, steric fact, I mean more amount of reactivity as compared to this one. Done. Next. The data suggests that in case, if at all I have to react Cn minus as a nucleophile to all these different carbonyl groups here, check out all these different carbonyl groups. What has been observed? First, let us analyze all the benzaldehyde cases. These are all benzaldehyde cases. In benzaldehyde withdrawing group like NO2, it has increased the K equilibrium. That means the reaction is happening faster. Then this one is okay. OME pushing it so much that the rate is decreasing. The minute the aldehyde from aldehydes, if it turn into ketones, the reactivity drastically decreases. And I told you, when you have two phenyls, very, very small, it is not even expected to make any reaction. Even if you have one methyl, one methyl and one ethyl also, the reactivity is quite less. Aldehydes are sufficiently more reactive. Formaldehyde extremely reactive. Now notice, if you have CF3, that means very strongly withdrawing group, then the K equilibrium is quite high. And if you have CF3 on both ends, that is also very, very high value. So here the polarity is an important role. Very high polarity will make this to have high reactivity. Okay. So have you noticed from the data some important point that generally all aldehydes are more reactive than any smallest of the ketone. Okay. So if I have to compare the NAR here, nucleophilic addition reaction rate, then in this first case, if this is A, B, C, definitely C is greater than B is greater than A, because CF3 is strongly withdrawing, CCl3 is also strongly withdrawing. Here there is no withdrawing groups. Second, if I compare A and B, definitely B is greater than A, because in benzaldehyde there is a resonance stability. Similarly, ketone versus benzaldehyde, if this is A and this is B, in that case, benzaldehyde still will be more reactive than ketone, because all aldehydes are generally more reactive than ketones. Now, comparatively, if you have an open ketone, open chain ketone, or a closed chain ketone, in that case, between A and B, closed chain ketone will always have more reactivity than open chain ketone. And then lastly, in case if you have, you know, ABC here, where we have a three-membered ring versus four-membered ring and five-membered ring. See, if you compare these three rings here, you would notice that A is more reactive than B than C. Why is that so? Check out. In three-membered ring, this carbon is sp2 hybridized, highly strained. And the minute if you add an nucleophile here, that carbon would become O minus and Nu, which is sp3 hybridized. Okay. So there is a huge strain released here. Strain release. So due to strong strain release nature, this cyclopropanone would be more reactive as compared to that of cyclohexanone or cyclobutanone and so. Only the case differs slightly when you have cyclopentyl group versus cyclohexyl group. In that case, we are expecting cyclopentyl, but here the reactivity changes. So here cyclohexanone is more reactive than cyclopentanone. There is sufficient reason for it. I mean, there is a good reason for it. I'm not getting into too much details of that, but in case if it is given, just keep this order intact, that three-membered ring greater than four-membered ring, greater than six-membered ring, and then it is greater than five-membered ring. This is the order you would follow. Everybody clear? Please check. Okay. Please check it out once quickly. What are all the uh, equilibrium data and how to compare the rates? Please check.